So actually, today I want to have this discussion on bridge engineering from a very different perspective. A long time when I arrived in Thailand many years ago, I went to a bookstore. I think it was called Kinokuniya. And on the shelf, I saw many books over there which were talking about architecture, but they were not for the architects. Those books were for the public to understand what the architects do. And I was surprised to find that there was no book about structural engineering on what the structural engineers do, because the public doesn't seem to be interested in the technical details. And I thought, oh, we should write a book on that. So I started a book called Bangkok Through Its Bridges. And that book is not published yet. We are still working on it. But during that time, I had the opportunity to visit most of the bridges in Bangkok and understand what bridge engineering is all about and how it is practiced in Thailand. And I think Thailand and Bangkok especially has a very deep understanding of how the bridges are designed for various purposes. So I thought today that we are going to have the introduction to bridge engineering, why don't we do it through the bridges of Bangkok? And we also discuss the development of the bridge engineering itself, because it's a nice history and it's a nice background. So with that, let me start the discussion. So the first point I think I always try to make in many of my presentation is that the physical infrastructure is the backbone of modern society. That means everything that is built is very important for the society to function. And the physical infrastructure, especially the bridges and the MRTs and all of that, is very, very important. So bridges are very essential in this system because they are connectors. They connect bridge is supposed to be, by definition, bridge means something that connects two things. And people use that in any context. So for us, bridge is a physical structure that connects something which is otherwise disconnected or is not connected properly. So this is both symbolic as well as functional. So with that definition, if we continue with the discussion, so if I look at the bridge project is actually much different from a building project, very, very different in as the way the bridge project is managed. And one of the key differences is that bridge project is normally managed by the state or the government or the public agencies. And it's a long-term public facility, unlike a building which may be designed by somebody, constructed by somebody, by a developer, then sold to somebody, then other people reside in it, and buildings keeps going through that. So there's no real owner of that building in the end. People who live there actually are not involved in the maintenance and upgrading of that building, but bridge is different. For the entire lifetime of the bridge, it is being managed by a single entity generally, or two entities if it is a build transfer project. So if you look at the build bridge project, it has many aspects. It has a life cycle that we will show a little bit. It has structural forms, many different materials, several components, construction materials, construction methods, analysis types, and uses of the bridge. So it's a very, very big spectrum of the bridges that we need to deal with. So it's more complex in buildings in many ways. And bridges are also an engineer's project, unlike buildings where architects are probably the main designer. Bridges often have engineers that design, although these days architects are getting involved because aesthetics in bridges is becoming so important. So if you look at many modern bridges, they are actually conceived by architects first, which is a sad thing because engineers are losing this very important aspect of structural engineering. So I will talk about aesthetics also a little bit towards the end. And if you expand each of those items, you will see further details, and we can keep on expanding it to infinity, because everything has so much detail there. So for example, in materials, we have composite, concrete, steel, masonry bridges. In Lifecycle, we have so many steps. In the components, we have so many components. For the bridge types, we have so many bridge types: pedestrian bridge, river bridge, and so on. So everything, if you expand, it goes really deep. And all of them are interconnected somehow. So understanding the whole bridge project goes way more than finite element analysis, or way more than just learning to use CSiBridge or just learning to use one tool. This is a huge undertaking. And as we get involved in this project of this endeavor, we will see that there's a lot more to do than just being engineers. We have to be designers and even artists, as I will discuss. So that's the overall bridge project. Very quick view of how big this scope or the spectrum is. And emerging technologies are now coming to sort of cover all of this. Emerging technologies, new technologies that we see, they are coming and affecting every aspect of this bridge. And we are, especially at CSI Bangkok, our role is to bring these emerging technologies into the bridge design process. So that's what we are doing, our research and development. So everything that we are doing is about bringing those in, and we are revisiting the programs to make sure that we incorporate these emerging technologies to make our work better, both in terms of how we work and the end product. So if you look at the bridge life cycle and the phases, it's a long one. It starts from feasibility studies, site investigation, and so on, all the way to rehabilitation and then decommissioning or deconstruction of the bridges. So it has so many steps on the way. We don't have time to go into every step, but we should recognize that we are dealing with a long process spread over 100 years or more of a bridge life. So we have to be careful. Any decision that we make today will affect the bridge in 100 years or 75 years. So it's not, many times we think about very short-term decisions on cost and sizing, but it affects the bridge performance over a very long time. And so that's why it's important that we understand where our position is. So we are doing the final design and detailed engineering. In this, we are learning about that. Of course, you are also involved in the construction, bidding, and many aspects, but typically consultants are only doing that part. But there are a lot of other things that we should also be focusing on. And the CSiBridge Express and other programs that we are developing are going to expand this from only the detailed design to other aspects like cost estimating, budgeting, preliminary sizing, and I will talk about that a little bit. So we are trying to make sure that bridge engineers have more control or more role or more active participation in the bridge life cycle, not just the design part. So we can go into all of that with using our tools and the technologies. We can cover most of these aspects of the bridge life. In fact, all of them, almost all of them. And as a contractor, construction firm, you're also involved in the construction process. So your role goes even beyond that one. So if you look at the stakeholders in this life cycle, there are many. And that's another thing. Understanding the stakeholder is key to what we are doing. Often we, as engineers, are quite narrow in the thing that we are just doing what we are given a task, but we forget sometimes that there are other people who have other interests in the project, nothing to do with the finite element modeling or analysis or nonlinear or what element we use, which software they use. They actually don't really care about that much. They have other interests in the bridge, financial, long-term maintenance and so on. So we should understand other stakeholders and their interest in the bridge, because we are the key people doing the design, which everyone else will be using in the end. So we have to work with the geotechnical consult, government agencies, and regulatory bodies, and project managers, and so on. So we have to deal with a lot of them while we are doing this project, during design and also during its rehabilitation. So bridge design, as I was saying, is a science, is an engineering process, and also an art, because now you will see, if you go to internet or to Pinterest, if you use that platform and say bridges, you will see all kind of, they only show beautiful bridges, because now somehow beauty and art somehow is also part of the bridges. Bridges in Dubai, bridges in other places, they're just masterpieces in art, not in engineering and science at the same time. So we should start thinking beyond the design process. Okay, coming back to Bangkok. So Bangkok, as I was saying, that is sort of get this inspiration to make this presentation. And if you look at Bangkok, people call it City of Angels, but for me, it's a city of bridges. Because there's so many bridges in Bangkok that you don't see in many cities, and there's a reason behind that. If you go to more developed countries, Singapore, Europe, or America, they prefer to make all their transport systems underground, because they are concerned about the spoiling the city's landscape. So it's not permitted. Like in Paris, it is unthinkable that somebody can make a flyover or an overhead expressway. It's just not thinkable. Similarly, in other countries. But in Bangkok, we see a lot of these structures above ground. But because we have the soil problem, we have the tunneling problem, we have other issues, and also the cost. So because of that, a lot of our transportation system, mass transit, and as well as expressways, they're almost all above ground. And that, another one city which has it is Los Angeles. They also have most of the things above ground. But anyway, so in bridges, and the other reason is that we have a big river flowing through the city, which is bisecting the city into two parts. So we have to go across, so we need bridges. So that's the reason that I think this is a city of bridges. We have bridges over the river. We have bridges for expressways, tollway, motorway, bridges for flyovers, so many flyovers, bridges for SkyTrain, monorails, bridges for the klongs. We have so many klongs in the city, and we have pedestrian bridges. So we have all kinds of bridge usage in the city, just in one city. And that's a very good, I think, learning opportunity for anybody learning bridge engineering. Okay, so just to let you know that most of the pictures are here. I went to these bridges to took them, unless I noted otherwise. Okay, so let's start with the bridges on the river Chao Phraya. This is a little bit old document, so it's missing one or two bridges. But if you look at that, there are so many bridges that cross this river because it goes through the city in a very interesting snake-like form. So it divides the city, not just one line, but in many times it goes in and out in many ways. So if you look at the bridge, look at the river, by the time it reaches the ocean, it has gone through many districts in Bangkok, or nearby districts. So we have, I think, about 18 or 20 bridges on the river itself. That's unlike many cities. They will not have so many large bridges within a city. A few, but not that many. And this is just to show you where they are located in terms of from the right-hand side is the ocean side, and the left-hand side is going northward. So we have bridges, total 19 or 18 if you count one of the bridges that crosses the river twice. So if you count it one, it is 18. Actually, it's more. We have just two more. So it's a little bit old data. I stopped writing this book a few years ago. So over 80 years, these bridges have been made. So we can see the development of the bridge engineering if we just follow these bridges. So we have steel bridges, we have concrete box bridges, and we have cable stayed bridges, a lot of them. So if you look at the bridges in terms of the time, the first one was 1927, the Rama 6 bridge, which was a steel truss bridge made for the train. It's no longer there, I understand. It has been replaced by a new expressway. I went there a few days ago and I couldn't find it. And then we have other bridges, most of them steel in the beginning, and then in concrete, and then cable stayed, and so on. So you can see where they are located on this map. Then we have the distance from the ocean, from the sea. So we have the first bridge about 15 kilometers, all the way to 88 kilometers along the river, passing through Bangkok, as well as its neighboring provinces like Pathum Thani and Nonthaburi and so on. And then the span of the bridges varies from, I think the main span from 485 meters. Actually, the other one, not the new one, is longer than this one, but until that, 485 meters, which is quite large, to 192 meters. So as the bridge goes northwards, it becomes narrow. As it goes south, it becomes wider. So you can see the bridge width also changing to accommodate that bridge flow. So we have every good range to study the bridge, the suitable bridge span. Okay, so let's start with the steel bridges on the river first. So this is the Krung Thep Bridge. It's a beautiful bridge. See, this bridge, and in the beginning, the problem was navigation. So they made several bridges which were openable. That means the center span of the bridge could be lifted or open for the ships to pass. And this is one of those bridges where you have the center span lift up to open and so that you can see over there. The Memorial Bridge has the same thing. That portion in the middle that you can see, this truss, two cantilever trusses, they can be lifted to open the bridge for ships to pass. And this was done at that time because high bridges were not practical. So they had these steel bridges. Most of these, 2 or 3 of them, had this opening or lift up spans. Then you have the Krung Thon Bridge, very nice truss system. Again, this doesn't have a lift-up span in this one, but it's a steel bridge, steel arch bridges, very nice. So you have different types of arch bridges here. And then you have the Rama 6 bridge, which was the first one, which was for the train. And it's a very simple, straightforward bridge. It is more on the north side. And you can see here very high truss with a very large depth to span ratio because of the large loading from the train. So that's the bridge that was built, probably the first one to be built. Then we move on to the concrete box girder bridges. And then this is when they started to build the first box girder bridges. In fact, most of the bridges in Thailand have been kind of a record during their time when they started. So one of the bridge at that time, Rama 3, was one of the longest, not the longest, but one of the longest at that time on the cantilever box girder bridge. And similarly, the Rama 9 bridge was also one of the longest single plane cable bridge at that time. So there are many kind of world records, if not completely, but temporary records when they started. So this is the Rama 3 bridge that I mentioned to you. This is a box girder bridge, very nice, beautiful bridge with a curve and also a high elevation. Now you can see that now the bridge is very high, so the ships can pass underneath that. All of the new bridges, the elevation is now higher to allow the ships and the goods to pass under them. And this is the Thaksin Bridge. This is a very interesting bridge. It's right in the city, center of city, and you can see the pillars are the two pylons are in such a way to reduce the main span and reduce the depth. So you can see that those V shape have actually helped to reduce the main span. And now we have a train also passing over that. And this is the Pink Claw Bridge. And Pink Claw Bridge has a center, is a very interesting bridge because it has a joint in the middle. It's also balanced cantilever, but unlike other Rama 3, it actually has a break in the center. There's an expansion joint. And if you go on that bridge and you stand on the bridge, every time the bus will pass, you can see the vibration shaking under your feet. And if you stand, put your legs, one leg on one side and the other leg on the other side of the joint, you can see the differential vertical movement there. And this, actually there's a misalignment in that bridge. And I went inside the box girder one time to inspect it because we will see why there's a slight misalignment. So there is a lot of work to be done when the bridges have these movement joints in the center. This is the Rama 5 bridge. It's also a box girder. A lot of cantilever box girder bridges, balanced cantilever meeting in the middle, so many of them. These are very complex bridges to design. Stage construction is very important. So for all of these bridges, stage construction analysis, long-term analysis, time-dependent analysis, they're all very critical. This is the Rama 7 bridge next to Rama 6. So you can see from here the old bridge on the background, the old steel bridge, which you cannot see now anymore because now they built another expressway around that. But at the time I took this picture, the bridge could still be seen. So you can see an old technology, 1927, and a new bridge next to each other. You can clearly see the difference between them. You can see how the steel bridge truss is a hinge at the support, whereas, so that bridge actually has a small cantilever and then hinge suspended span. Rama 6, the design of that was very interesting because it has the span and then there's a small cantilever of the truss and then the central span resting on those cantilevers to reduce the height or the span of the suspended span. This is Rama 4 bridge, the first one on the north, if you come from that side. And now let's move on to cable stayed bridges. So every bridge that I showed you, when we have more time, we can see a lot of interesting design challenges in each one of them, which I will show, a few of them. So Rama 9 was the first cable stayed bridge constructed. In fact, I was a student at AIT at that time when this was being designed and built, and our professor, Dr. Wieland, was involved in the design there, and also one other professor, Professor Brigado, was involved in the foundation professor. So we have all faculty members involved in the design of this project in many things. And I remember going to the river on a boat on the day that they were going to connect the two sides, because two sides of the span, they come and connect in the middle. So it's a balanced side. And you have to connect them exactly at the right time and temperature, because if the temperature is too long, bridge will expand and they won't connect. So they had to wait for the right temperature, right time, and had maybe an hour or so within which they have to weld the two sections, this is steel section, weld them together. It will be very interesting to watch that happen. So it's a huge challenge to making, and the pile cap for this one was so large, So anyway, so this is one of the interesting bridge, single plane, one of the longest span single plane bridge at that time, because it doesn't have two, so it has a lot of torsion, as you can imagine, in the deck. So it was made of a steel box with the triangulation in the box. This is the mega bridge. This is actually two bridges combined together. They cross the river twice. So you have two of the cable-stayed bridges next to each other, crossing the same river two times, which is very interesting because you have a loop and it just crosses the river twice in a very short time. Very beautiful bridges when you drive on them. And you can see the architecture changing and the local architectural context coming into the bridge design, the symbolic architecture from Thailand. And this is the Rama 8 bridge, beautiful bridge. The beauty of this bridge is that this is in the city, very low. So you can actually walk on it, unlike other bridges. You can walk, there's a nice walkways and you can go and experience the bridge on the top, on the bottom. And it is single plane on one side and two cable planes on the other side. So it's a beautiful bridge. Normally, most of the marathons in Bangkok, they always run through Rama 8. And I have joined a few, so it's really nice to, so normally when I'm running on the bridge, I'm hardly running, I'm just focusing on the bridge itself to see how beautiful it is, because when you run from one side to the other, you see two cables changing into one plan. I think it's a beautiful bridge from every angle, because a single pylon bridge and two sides, two spans, main span on one side and the other one is just anchor. This is the Kanchapesic bridge. This is the longer, I think, than the Rama 9. And it's on the more south, probably the most south bridge in Thailand, in Bangkok. And once again, the architecture is now getting more localized. It's beautiful, once again, very long span and very, very nice bridge. And recently, just finished, I think a couple of months ago, is the new bridge, which is just next to the Rama 9 bridge that was constructed earlier, because the traffic became so large that Rama 9 just couldn't handle it. So they had another cable-stayed bridge, but this time with two pylons with more architectural components, because like I said, more architects are getting involved in the bridge design, so you can see the effect of the architecture. One is pure structural on the left-hand side, simple steel column, nothing. The right one is more architectural with spans, that link between them, So you can see the evolving bridges. I think they're 30 years apart, something like that. So you can see the lighting on the bridge and all of that stuff. So it's pretty nice if you go there. And every time they open a bridge, there's always a marathon running across the bridge. So there was on Rama 9 also, there was a marathon, and then there was another one when they opened this one. So it's very, very interesting that they open it with a pedestrian run. Okay, I just want to show you now bridges next to each other because they say a lot about the structural system, about how engineering has evolved. So you can see here several bridges next to each other. And it also shows the expansion of the traffic in Bangkok, because they made one bridge and suddenly they have to make another bridge exactly at the same location or next to either, because the traffic just keeps on growing. So I was saying that bridges are so important for the economy, because as the economy grows, the city grows, the first thing you need is more bridges, more expressways, more subways. So these are the few bridges which are each next to each other. And let me show you. This is my favorite picture of the bridges. I took it on the old bridge side. So if you stand there, you can see the joint in the middle where the bridge is lifted up. So it's a joint and it vibrates so much. If you stand there, when the cars pass on it, you can feel the vibration because it's a cantilever from both directions. And the other side I'm looking at is the Rama 3 bridge. And behind that, you can see Bangkok. So this was the title of my book, Bangkok Through Its Bridges, because you have like an eye forming between two bridges, and then you can easily see the city growing behind that. So that's a real picture. I didn't Photoshop it. This is the real picture. So this is how you can see the one bridge solved the problem of the waterway by making it openable, and the second one solved it by making it very high. By the way, if you notice the truck on the bridge, Rama 3, is the same truck. There are not three trucks, because I took the pictures through side with many slices and then merge it together. So same truck is passing, and you can see it in 3 pictures. So it's not 3 trucks; it's the same truck. While it was moving, I was taking picture and then stitched it together. So that's why you see that. And this car also is the same car on both the sides, not 3 cars. Okay, so this is another way to look at the bridge. You can see look at the column of the 2 bridges are aligned. One is a truss on the one side, other one, and then look at the difference between steel and concrete. On steel, at the support, we try not to have any bending moment, so we put them as hinges. So the truss goes down to 0 height, but on the other side, for the concrete, we try to take advantage of the negative moment because it's a cantilever bridge. So the height of the bridge is the maximum at the support, whereas the height of the bridge is 0 at the support for steel, and that's the typical way that steel trusses were designed, simply supported with pure hinge and roller supports, whereas the complex box girder bridges have these continuous spans with balanced cantilever, sometimes unbalanced. So the other bridge you can see here, I'm sitting on the steel bridge, I think Krumthon, and I'm looking at the Rama 8 bridge. That's also a very nice 2 bridges you can see from there. And then on the left-hand side is a nice picture at the bottom, because the alignment of the truss and alignment curve of the Rama 3 bridge are very well aligned from this angle. You can see the same curve in the truss. And these are not accidental. These are all part of the engineering process. Every decision here is based on some engineering, and it happened to have that symmetry that we can see from here. So it's not just finding, you have to design the whole thing, keeping everything in context. This is another beautiful picture, I think, but one side is the old bridge, the second side is the new bridge, and it's a very nice way to look at 2 different technologies or 2 different ways of doing the same thing. This is another picture from the Rama 7 to 6 on the bottom, which you cannot see anymore, as I mentioned to you. This is another picture of the Rama, I forgot the name on the left-hand side, and the Krumthon bridge. So these are different bridges, as you can see, and the evolving of the bridge engineering over the years. And these are the 2 bridges, the one that I mentioned to you, the Rama 9 and the new one, and you can see them side by side with the K-Bank building behind it and the plan also there. So you can clearly see how the 2 have been. The Rama 9 has had problems since its construction because of the large cantilevers around the central cable plane. And so it has always had some problem on the surfacing not attaching to the concrete, it's concrete not attaching to the steel box and so on. So there's been always something going on with that bridge. And I think that's why they made the new one in the different concrete, all concrete. Okay, let's move on to the expressways. So expressways, there are so many expressways in Bangkok. And I arrived in Bangkok first time in, I think, 1986. And at that time, there weren't any. So if you want to go from AIT to Bangkok, or anywhere, you just have to wait. Sometimes it took 7 hours, 5 hours to just cross the city. But now we have so many expressways constructed during that time. Okay, so this is the expressway map of Thailand, and these are the lists of the expressway with the listing, with the operator, and I took it from the BEM website. And then the distance of each one. So there are about 275, this is in 2003, 275 kilometers of expressways in the city. So which is quite a lot of bridges. They are all elevated bridges. So you can see 270 kilometers of bridges, just bridges, all kinds of bridges, not counting the flyovers in the city. So that's a lot of bridge to be designed and constructed, maintained, and monitored. So if this is a picture from, I think I took it from the Bayok Tower, one of the expressways intersection, Ding Dang, I think. So that's what you can see, how the complex the layouts of these bridges are and how complex the arrangement can be. So this is another interesting bridge in one of the expressways, which is the Bangna Expressway. And when it was made, I think it was the longest bridge. It probably still is. It's 55 kilometer long, one single bridge, going from one to the other place. And there are thousands of spans in there. This is probably one of because I worked on this bridge foundation for a while, and so it was being designed. We looked at this one. This bridge is so interesting because it is designed by a German company, and they optimized it to the maximum. The box girder is very big, 6-lane box girder, but it's very empty, just a truss inside. The columns, the bends or piles, piers are highly optimized, very, very efficient, because whatever saving they made, it multiplies to 55,000 times. So they really optimized the design of this bridge in every way. I think to the last rebar, highly optimized this concept, design, system, and everything. So it's really very impressive that you have a very light bridge to supporting 6 lanes of highway on top. Very, very interesting bridge in my opinion. So then we move on to the mass transit system. And this is now the new, everything is developing in mass transit. We have so many lines coming up every day, some underground, some above ground. And sometimes I travel and I look at them, I feel that the bridges that we are designing are not pretty. They are spoiling the city's landscape a lot. And I have many pictures which I feel that things could have been done better. But anyway, so let's look at that. These are all of the lines. This is a plan until 2025. And you can see all of the plans of the MRT, the mass transit lines, both underground, above ground, all colors. Colors are finishing actually now. We have all kind of colors here. And they are running all the way very far from the city. You can see they go very, very far now. And they are constructed, of course, in all kinds of bridges. And so so many stories during the construction, but let's look at that. This is the first SkyTrain project, I think finished in 2004 or something. And the segments this is a segmental construction. Each span has, I think, 16 segments. And they were manufactured somewhere near an AIT. And I remember we used to see 16 trucks carrying one segment each going to Bangkok every day. And every night they will assemble one span of the highway. And they only have 6 hours or 5 hours to do it because the traffic can only be stopped at night. So within 4 or 5 hours, they will construct one span, bring all those segments, put them up, post-tension them, and be done with it before the morning. It was, I think, it's amazing because they built this one in the middle of the busiest roads in Bangkok, like Sukhumvit and so on. And it was just amazing. So we watched this being constructed, and it was quite interesting to see that it was done by running traffic. And another project that really fascinated me actually was the Don Mueang Tollway. So first part of Don Mueang Tollway was constructed when I was a student here, and in 1988 it finished, and that was between the old airport to the city. And it was just, and I remember that on that project, they wanted to, another German company designed it, and they wanted to remove the diaphragm because they said that we don't want to use diaphragm because if we put the diaphragm, it will delay the project by half a year and then they did a lot of analysis, actually in AIT, using a program called Microfibre 2 to find out whether the diaphragm can we do without diaphragm or not. And you will see that many spans in that expressway don't have a diaphragm. And then the second part of that was constructed from the airport towards AIT, to Rangsit, during the 1997 Asian Games. And they finished this 13-kilometer long bridge in a main highway in 13 months. And I thought that is an impossible thing to do. And just 3 months before the Asian Games, I saw many kilometers still left, but I don't know how. But on Asian Games Day, the bridge was open. So it's amazing. So those two, the Don Mueang Tollway, 2 parts, are a very interesting story. This is the monorail now. I see that being constructed many places, and you have a single girder. You see, unlike the SkyTrain where you have a box girder and it supports the rain, the monorails are supported on a single girder. This has a huge problem in stability, in torsion, in everything. So, compression, the buckling, torsion, So there's a lot of things to consider for bridges of this kind. And they are very, very sensitive. And now they are being constructed everywhere for the new projects. And I think many of them, in my opinion, could have been more, architecturally improved, so to speak. Anyway, Let's come to the pedestrian bridges. So pedestrian bridges are everywhere in Thailand, in Bangkok and surrounding. I just actually missed a few concrete ones, but these are the steel ones, and you can see how they are, they are placed, and there are some other interesting pedestrian bridges, many places, especially now the skywalks, so many skywalks connecting one station to the other. So many new pedestrian bridges are coming up. And this is an interesting one on Sathon. I don't know if you've seen it or not, but if you haven't, please go there and then walk underneath. It's a very beautiful bridge. A lot of people go and take the one at the bottom, the yellow one, and some other pedestrian bridges. So you can see there's a lot of opportunity for creative expression in pedestrian bridges. Okay, so now that we have gone through the Bangkok's bridges as a summary, let's look at the challenges that engineers have faced, and they have found solution, and something that will show us the complexity in the design of these bridges in an urban environment and the construction. I think this is just unbelievable how this thing is done. Okay, but before that, I recommend this book to everyone in my class, and also to everyone. If you can get hold of this book, please read this, The Tower and the Bridge. This is a beautiful book talking about the art of structural engineering, both for tall buildings and for the bridges. And this is a classic bridge, I think, with Christian Men in Switzerland. It's a beautiful bridge which combined the concrete with the cable stayed concept. The only bridge that did that kind of thing, and put it on a curve. So it's a beautiful book, and it's an old one, but it's still useful. Okay, the bridge system. So I'm just going to scan through quickly. So we have beam and frame type bridges, we have arch type bridges, we have tied arch type bridges, and then we have suspension and cable stayed bridges. So I don't need to go into a lot of detail here. I just give you some idea, and we are going to look at them from the Bangkok bridges side. The bridge also has a lot of components. We have a deck with slab, girders, diaphragms, and so on. We have substructure with transoms, approach, cables, piers, pylons, and so on. So we have a lot of components in the bridge that we have to model, analyze, design, construct, of course. And there are many ancillary components like barriers and drainage and lighting and so on. Okay, so the biggest question in bridge engineering and any structural system is, how do you choose which system is the best? Because you have so many options from the structural forms of the components. So which system should we choose? What should be preliminary sizing? What will be more efficient? What will be more economical? Which will be made faster? And so on. And many of these bridges are on build, operate, transfer project. That means somebody puts the money in and then transfer to the government. So they are trying to save every baht or satang they can from the design. So it has to be really efficient. So system selection has to be done efficiently, and that depends on so many factors. But of course, as you know now, AI is here, and AI can definitely help us in this part. And I will present towards the end one of the tools that our team and students at AIT have developed, which I think you have seen before also, but I will show that anyway. So we have explicit learning from experience, the first one, which is what we're doing now. By looking at the bridges data or bridges that we have already seen, we can learn from that and select the next system. That's the learning from experience of others. The second one is AI system based on synthetic data. That means we can generate data, valid data, that can then be used, or real data, together, and then that can be used to make the decisions for the design of these, or system selection for these bridges. So let's go back a little bit and look at the bridges again with the Bangkok in context, and we'll come back to this one more time. So if you look at the truss forms, I showed you already, we have several truss forms. Most of them, truss form, have a pass-through design. That means two trusses on each side connected together at the top. So it's like a pass-through truss system, which is very efficient because it prevents the buckling of the trusses in compression. So the top flange is connected and continuously, so you don't have a problem for the buckling. Otherwise, if you put the trusses independently, don't connect them, the truss can buckle in compression and will not be stable. So that's why this system is very efficient and has been used in all of the bridges. And that's the sketch I did that sketch just to show how that bridge would have opened during the opening for when the traffic was passing over there. So you can see that the cantilever truss is different design than the main span behind that. And two cantilevers meet together. It's very interesting because the next bridge is also a balanced cantilever, concrete box girder. It's just that it doesn't open, but the concept is the same. The two cantilevers coming from the sides and meeting in the middle. So exactly the same concept as this one. So like I said, the people who designed that bridge looked at the bridge and then looked at the design from that angle to making sure that there is some relationship between them. This is just the connections. You can see here, how the members are connected to each other, and then you can see also the suspended span concept, that you have half the spans coming from this one, and then you have a suspended span in the middle, which was used for Rama 6 bridge. Now let's look at some deck systems. So these are the deck system used in the bridges that you have seen so far. So there are several box girder, and then because these are all bridges on the river, so they're long span. So you cannot use eye girder or something. So there has to be a truss, or has to be a box girder, or has to be a cable straight. So at the cable straight bridge section, you can see there's a steel truss deck for Rama 9, and there are a steel beam for Rama 8 with the box underneath to cover it. So there are for other bridges, then you have the steel pass-through truss. So there's nothing below that. So deck is here, and the truss is above that. So concrete bridges, the bridge is below, the structure is below the deck, but for steel, the structure is on the side or above the deck. So that's the key difference that you can see from here. Now look at that. The one on the left-hand side is a steel eye girder bridges and with the concrete slab. And these are mostly used in flyovers in Bangkok. In fact, there are 13 of them, if I remember correctly, that were made very quickly. One flyover in 3-4 months, if I remember. I think the Japan Thai or Ital Thai, one of those. They really made it very, very fast because they just put the steel column. So the column is steel, the bracket is steel, the crossbeam, the transom is steel, girders are steel, and then just put the diaphragm is steel, and thus the slab is concrete. And these are many of them. The problem that we are facing with these bridges, as you might know, is the vibration. Many of these bridges have a vibration problem, which is being observed. There was this recent study by one of our colleagues from in AIT. They did all of the instrumentation, and they found that the vibration in many of them are being retrofitted at the moment. So if you go on, especially on Rama 9 Road, you will see that the flyovers are being retrofitted to reduce the vibration. Also, they require a lot of maintenance, repainting, and so on. Concrete, on the other hand, doesn't require a lot of maintenance except at the bearings. But you can see that the concrete, almost parallel, you have the diaphragms, and you have the concrete girder, and then you have the main transom. So you can clean. On the right-hand side, on the top, you see the box girder, the same arrangement, and it's much more clean. Box girder is just 2 webs normally, or 3, and then you have the nice clean surface, and everything is inside. You don't see anything. Diaphragms are inside, if there are any. And then it's very good for curved bridges. But what I want to show you is the right-hand top and bottom picture. The top one is a curved bridge in box girder which just flows through quickly. For a similar curved bridge at the bottom using eye girders, you have to do, as you can see here, that you can't curve the beams. So beams are straight. So that means the slab has a variable cantilever from the sides on that one. And at some location, the slab may come inside the girder. In fact, when we are developing the CSiBridge Express and we curve the bridge, we find there's this problem that the straight bridge goes outside the deck and we have to adjust the deck width. Also, second thing you will notice is the capping head on the column. So for the box girder, there's not a problem, but on the right hand, the one on the right hand bottom, they tried to keep the girder length the same, so they changed the size of the capping slab or the pier head, and make it unequal on both sides. And so there's a very nice trick to keep the girders of the same size and design rather than changing the length of each girder, which will be the second option. So this is some of the interesting things that we can observe from these bridges. This is an interesting thing for the cable-stayed bridge, where you can see the approach slab is in concrete, and after the main span starts, it becomes steel. And that is understandable, because for the main span, you want to reduce the weight as much as possible, because cables are so expensive, you don't want a heavy weight. So that's why as soon as the main span starts, and those expansion joints between the approach slab and the cable-stayed bridge are designed to handle very large axial expansion due to temperature. It could be as big as 300 millimeter or 200 millimeter. So during summer and winter, day and night, the main bridge will expand and contract. And all of that expansion contraction has to be accommodated close to on this joint that you see over there. On the right-hand side is the Rama 8 bridge, which is very smooth. They covered it up, and inside there are eye girders, but they covered it up with the smooth soffit, because it's in the city and it's very low, and you can actually stand there watching that. So that's the other bridge that you can see. So cable-stayed bridges have this interesting design for their decks. Now let's look at the pylons, piers, and pier frames. And this is where you will see things get really, really complicated in bridges. So in my personal view, designing the deck is one thing, and designing the substructure is totally another challenge. Because deck you can standardize to some extent. Spans can be similar, and it's not much you can do. But for the substructure, every substructure may become unique, especially in the city, and then you will see here. So first of all, let's start with the cable-stayed bridges. So you have pylons, and you can see here the Rama 8 on the left-hand side has an interesting design. The other two bridges, new ones, have a different design of the pylons, because for Rama 8, one side is single plane, one side is double plane. So they use that single pylon in the middle and then V at the bottom. And the others one are using the V-shaped for both the sides. And that's another one. This delta form for the cable-stayed bridges is very good pier form, because it's so efficient in every way, and it just, as you can see here, it can be made in very economically. And then you see those Y columns matching with the delta form at the approach side, because approach side is small span. So you don't need a very large span, but you need to anchor the cables which are coming down from the main span. So they have to be anchored here, so it will not lift up. So those are mostly anchor spans or anchor piers, and they could be actually in tension. So that's the side, and then you can see here for the Rama 9 bridge, it's a different design. The approach panels are not the same as the one in the new bridges. This is the underneath of the bridges on the mega bridge, section in between the island. And if you go there and you look up, you see this crazy movement of the approach approach spans and interchanges going on is so complex. You can see easily. And now you can see the challenges here. First of all, the columns are really, really tall. So slenderness, P delta effect, that has to be incorporated. And you might wonder, why did they make them so slender? And the main reason is that we don't want the deck to be affected by the stiffness of the column, and we also don't want the force, the moments to be developed in the column. So to avoid that, you need to make it as less stiff as possible, so it won't attract many moments. It will just attract like a prop. And the bridge stability is coming from its curvature, so you don't need the stability of the column to hold it. So it's just the bridge is stable as a form, but it's just propped up. So this whole, and a few columns are designed heavy to take out all of the forces. So it's a very complex arrangement of the substructure with very careful designing of which column is the anchor column, which is the prop column, which column we should allow movement, which column we should not allow movement. So modeling, obviously, of a bridge like this, bridge system like this, is a challenge, is a huge challenge. And this one, once again, the difference between various types of arrangement to support the deck. The left-hand side, you can see the most typical eye girder supported on a capping beam with the bearings over there. The one at the bottom is a picture from the Donmong Tollway, and you can see here, because of the road underneath, you have to shift the columns, and so the columns is now shifted, but then you need, the span is unsymmetrical, so you need another column on the other side. So you can see every column, you can see Y column here, next one is not a Y column, before that is a single Y column. So every bend, every pier may have to be designed uniquely to cover, and then the substructure has to be modeled, has to be analyzed. Mostly they are post-tension. So I think bridge engineers will spend most of the time designing the substructure for bridges of this kind. Box girder, on the other hand, is simpler. You can see on the right-hand side is just a single column, and we just support it bearings at the top. And once again, the substructure for the BTS, highly complicated, because they have to turn on a certain radius on the roads. So there you have so many big, huge cantilevers. Look at that column on the left picture, carrying two train tracks, all cantilevered. So imagine the bending moment in that column and the bending moment in the foundation to keep it stable. So it's a huge challenge to design. And so one side, the cantilever is on the right-hand side. Next pair, the cantilever is on the left-hand side. So every pylon, every column is very unique and uniquely loaded by different kinds of loading. And they try to keep it as architecturally static. You have to see the curve, you can see the slots, and so on, and rounded edges. So it's a good job. And you can see on the right-hand side also how complex it can be. So substructure of these systems, expressways as well as the MRTs, the mass transit systems, can be very complicated and requires special attention, long-term creep effects for the deflections, tilting of the cantilevers, and so on. Look at the left-hand side. You can see once again the steel, stepped girder, step box girder. So in the middle, you need to change the geometry of the girder because the two elevations of the two sides are different. So it's a off ramp at Sukhumvit from the main expressway, and you can see what they have to do to make that. And this pillar, the steel pillar, has to go under the existing bridge, and so on. So and then on the same thing on the other pictures on the right-hand side, they just don't have enough clearance. So they cut the bridge slightly on the right-hand side to fit those steel columns in there. And the steel columns must have been optimized as much as you can so that they don't have to cut the bridge too much and fit on the tight spot. So these are the challenges that the bridge engineers will face in handling the bridges in a city. And same is the case with the central one. You can see a curved bridge and with the tall columns with their pier heads. So once again, now let's start with the picture on the left top and left bottom. I want to show you the difference between the column size, why the column on the above picture is designed as big and why the column at the bottom is designed as so thin. Because there is a reason behind that. The one on the top is a simply supported two spans. So each span is resting on that pier, single pier, independent independent spans. There's a joint between them. On the bottom is a continuous bridge, continuous girder. So we don't want any moment to be transferred to the column, and we don't want the column to restrict the expansion or contraction of the deck, make it free. So to do that, the column in that plane must be as thin as possible so that it will just bend or move with the bridge without causing any bending moment. And the other direction, it needs to provide stability so it becomes like a wall. So all these decisions are very critical, and they affect the modeling of the structure, design of the foundation, design of the bend. Then you see those Y columns for the cable stayed bridges, and also how the drainage is included in the grooves in those columns. So drainage is a very important part of the bridge. It must come down. So it's better to put some space for the drainage and lighting to go with the column rather than hanging outside. Sometimes they put the drainage inside a box column. Once again, you can see here the arrangement of the capping beams, the pylons, the columns, and the girder, and so everything. And sometimes you have to accommodate the slope in the deck. So you can see the second picture below that. it also has a slope upwards. The above has to accommodate the super elevation. So you have to accommodate the curve part that also. Okay, so let's go faster a little bit. I'm told that I'm running out of time. So we have once again the new recent pylons and bridges being constructed. You can see the precast capping beam on those columns. All of them, they're using that kind of structure. It's very good. Okay, let's go faster. The one I showed you, the long expressway, beautiful design of a 6-lane on a single cell box with triangles inside and struts inside, and a very efficient. And the one on the down is a very new bridge you might or might not have seen, is for the high-speed train between Bangkok and North. So those are the columns for that, the bottom two pictures. Okay, foundations, I think I have to be very fast. So these are the foundations. You can see foundations for bridges are very, very large, especially for Cable Strait Bridge. This foundation is so large that it can, a whole building can be made from the concrete consumed in just footing. And it takes a lot. I remember when they were constructing, they have to stop the whole supply of concrete to the city. All supply must go to this foundation. So you can see here, huge foundations there. Okay, let's go the cable system. You can see the cable systems and how they're anchored. So you have to see how the cables are connected together during construction. And then we have bearing and joints. So one of the key challenges in bridge compared to building is that in building, everything is made to connect together. Nothing is supposed to move away. But in bridges, they are designed to move while transfer the load. So that challenge of allowing the things to move at the same time transfer loads becomes a challenge in bearings of the bridges and expansion joints, because you have to transfer the force but allow the movement also, and that's it. And that makes a challenge in construction, but most importantly in modeling, where you have to model these bearings as linear or non-linear. Sometimes these are real hinges in old buildings, old bridges, steel, total true hinge. And you can see on the left-hand side, the sliding, and then you have these bearings, all kinds of bearings, complicated bearings coming up. Some bearings high, some low. So you have all these bearings. You can clearly see them, some pot bearings, and how the expansion joint has to be provided for their movement, and how they allow movement in one direction, don't allow the movement in another direction, and so on. So you can see all these interesting bearings in the bridges. Like I said, that's the expansion joint in that center of that bridge, Pink Claw Bridge, and then that moves. So sometimes it gets locked, that comb that you see in the middle, that's the expansion joint, moving, closing, and so you can see sometimes completely closed, sometimes completely open, depending upon the day of the year and time of the day. And that's the locked, I was telling you, there's a misalignment on the bearing. So you see that on the right bottom. Talk about the statics in bridges a little bit. So this is this Rama 3 is a beautiful bridge. So the statics have been considered very nicely in design of everything in that bridge. So I think that shows there. So we must make sure that we make the bridges, when we design it, to form the flow, the aesthetics should be considered in all aspects. So there are some rules, as you can see this presentation later, how to proportion this one. So what we have seen so far is what we should do and also what we should not do by looking at the existing bridges, because you can observe the good things, you can also observe not so good things. So we can learn from this experience. Okay, future design trend. Now, because of the tools coming in, we can integrate the whole process. Before it was step by step, one step, transfer data, another step, transfer data, and so on. Now we have opportunity to integrate. So SAP 90 was made 50 years ago when people started designing bridges using SAP 90. At that time, it was, as you can imagine, a program that purely worked on text data files, no UI. So SAP 90 picture over there. And then from there, we have SAP 2000, which advanced a lot. And then from there, we have CSiBridge, which is a special version of the SAP dealing with the bridges. And now we have the new CSiBridge Express gradually in that transition. So CSI is developing these tools more and more focused toward bridges, more and more integrated with every step. So CSiBridge main can handle any bridge of any type, of any complexity that you saw before. So there's nothing CSiBridge cannot do if we model properly. CSiBridge, on the other hand, currently is focused on parametric design of girder bridges and plus box girder bridges in the coming version. So let's just take a quick look. So in the parametric design, you can start from the map, you make the design, automatically make the mesh, automatically do the analysis, automatically do the design, automatically do all the rebar cage, automatically you can transfer to Revit, you can do the costing, BOQ, and finally put the bridge back on the map. And then you can have the BOQs and the costing done. So the costing BOQ is integral part of the bridge because that is needed right from the beginning. So we can do that. Okay, let's take a quick look at the 3-minute video showing how the parametric modeling can help us to create the bridge completely, geometrically complete, step by step going. So you can see that the abutment is being modeled, and then you have the pylons and foundations and the girders and the barriers and the diaphragms. And so you keep on seeing how the bridge is built up from pure geometrical elements which are almost as accurate as the construction. So it's important that if other people are going to use these tools, we make the bridge complete. Not just a finite element model, but a physical bridge model should be as complete as possible so people can use it for drainage design, they can use it for lighting design, they can use it for management or anything. So the first task is to make sure that the bridge model is as complete or as complete practically as can be, ready for construction level of details. So that's the first thing. So we start from that end to make sure that the bridge will have sufficient detail. So you can see that now the reinforcement should be part of the bridge model, not designed later. You can update it, but we can put the reinforcement in the bridge at the time of modeling. So we already have the costing, we already have the BOQs ready. We also know how the bridge reinforcement cage will look like. And we can modify that without even going through the design to see what we need. So you can see the bridge, the reinforcement is all there in the model itself before we do any analysis or design. So this is the model of the bridge before we have done the finite element modeling, analysis, or design. So you can see that it's more or less complete in every way. And this is the modeling, second part now. How do we convert that into a finite element model which will be as good or even better that we can do manually? See, normally people use these bridges with using the frame elements. But in CSiBridge Express, we use the shell model and solid model to model everything because that's more precise and that's more matching more with the physical. So the physicality of the bridge is maintained by creating a finite element mesh which is very close to reality, including the abutments, including all the components of the bridge are included in the model, piles and so on, and soil and springs and everything. And then you can analyze it. From that shell analysis, you can extract the forces, bending moment, shear forces for the design purpose by using integration. And then you can get the forces in the substructure. And then you can use that information to design the foundation, design the columns, design the capping beams, and so on. So that's how the integration of the complete geometry to meshing to analysis will work. So that you can see here that all the things that I showed you earlier, then you can get the design forces from there, and the program should be able to design those substructure as well as not only the superstructure, but substructure components as well, all the way to piles. Okay, so this is the last slide, is the box girder coming up, not complete yet, but this is the next version of the CSiBridge Express, which we hope to finish very soon. So currently, basically, handling the box girder in the same way. So box girder modeling is normally more complicated because of the shape of the box girder. So we can create automatic mesh, also put the reinforcement in the box. And this is the same box used for many of the bridges in Bangkok. So you can put the reinforcement is already there. And then from there, once you have defined the segments of the box and set the geometry of the box, then it can be put onto the bridge itself. So that's the bridge. And then you put the box there. Now it's a box girder bridge. And you can see inside the box if you walk through or crawl through the box. And then the good thing about parametric design is that you can create a straight bridge and then just put it on a curved alignment. And you say, okay, I want a curved bridge, and the bridge will become curved, and all the things will just become curved without doing any change, just one step, and the straight bridge will form the curve and also the elevation. So it's a curved bridge with super elevation, or then you can just make it in few minutes by designing it for the straight and then just putting it any alignment. And because of the parametric modeling, it just gets everything. And you have the tendons inside, the post-tensioning, you can see, and this is the external tendons for this bridge. And then you can see them, how they will be anchored and how they will, you have the, so all these components are real. And then the model will take these real components and then create the finite element mesh and do the analysis. And then, of course, like I said, the rebar cage is already complete because we defined it from this superstructure all the way to the piles. So everything is in the model, and it just has to be confirmed by analysis and design. So that's the way that the parametric designs will work. The last item, I'm sorry, that was not the last item. The last item is the AI-assisted design. So this is the way that the AI can be used to carry out the preliminary design of the bridge, because the students here in AIT, he just finished last year, he used CSiBridge Express to design 7,000 bridges of every different configuration, then used the data from those 7,000 bridges and then created an AI-enabled tool where you can have a conversation and you can say, I want to design a bridge that much long. What is the most economical, optimum size of the girder, spacing, number, span, how many spans should I use, what kind of girder should I use? So you can have that conversation with this AI tool, like ChatGPT kind of thing, and it will give you many options that are possible. Then you choose one of the option, and then this option will be then transferred to CSiBridge Express for further analysis. So you don't have to start the model, you just use AI to do the preliminary sizing, you can modify here, and then it goes directly and creates a model in CSiBridge Express ready to run. So theoretically speaking, a bridge could be done in 10-15 minutes for the preliminary design. Of course, for detailed design, there's so much more to be done, but at least we can have the AI tools assisting us in that direction. So after that, it will be transferred to CSiBridge Express, and then it will be analyzed, just save time. So then it will be, all the reinforcement is there, all the design is there, everything is complete. So without entering any data, through a conversation with the AI tool behind the program, we can actually create a typical bridge model. Of course, this is not good for all the complex bridges I showed you, but it's good enough for starting a straight bridge, which can then be curved, which can then be modified in the program here. So with that, let me just stop. So with that, thank you.